Alright, let's go over the page 712 homework questions 53 to 65 and 73 to 77 odd. For the most part, I'm going to go through these fairly quickly. I just want to be sure that you understand how to set them up. I might not give you final answers for things, but at a minimum, I'll show you the setups. So let's start with question 53. Question 53 reads, lactic acid has one acidic hydrogen. A 0.1 molar solution of lactic acid has a pH of 2.44. Calculate the Ka. So let's start with the reaction the way I've written it. So you'll notice here that I wrote HLA. That's because I'm too lazy to write the whole formula for lactic acid. So what I do to save myself some time is I write La for lactic acid and an H in front because that's the hydrogen that I'm going to show being donated to the water. So in my reaction, I've got this lactic acid interacting with water, donating its hydrogen to the water, forming hydronium and lactate. And so the formula for lactate is just La. Again, I'm too lazy to write the real formula. I'm just writing an abbreviation with a minus sign. The initial concentration that I was given for the lactic acid is 0.10. For the products, is going to be 0 and 0 because I'm assuming that this is before it actually interacts with the water and donates its proton. Lactic acid I know is a weak acid. I can tell that based on the pH. So the pH is not anything close to 0 or 1. So I'm going to call this essentially weak. And so I'm going to use this value to figure out how much hydronium is left in the equilibrium line. So I know that the C line, I'm going to subtract from the left-hand side. I'm going to subtract X, and then I'm going to add X on the right-hand side. All right, so take a look. If the pH is equal to 2.44, and I know that the formula for pH is that that's the negative log of the hydronium concentration, I can calculate the hydronium concentration by taking 10 to the negative pH power. So the hydronium concentration is 10 to the negative 2.44 power. If I put that in my calculator and simplify, that value is 3.63 times 10 to the negative third. Okay, great. So now I know that 0 plus x is equal to 6.3 times 10 to the negative third. So then x must be 3.63 times 10 to the negative third. So then that's the value for the equilibrium of hydronium concentration. That's also the value for the lactate concentration. And then if I take this value for x and substitute it into the HLA column and subtract, then I'm left with 9.64 times 10 to the negative second HLA. Now I've got actual numerical values that I can substitute into the mass action expression to solve for Ka. And the mass action expression is going to be your hydronium times your lactate over your HLA. So when you substitute in 3.63 times 10 to the negative third. You square that, and you divide that by 9.64 times 10 to the negative second. So again, I'm not going to give you the final simplified answer, but that's the setup for question number 53. Let's take a look at question number 55. 55 is telling me that I have a 0.1 molar solution of chloroacetic acid. It's 11% ionized. And using this information, they want me to calculate the concentrations of the ions and undissociated acid and the Ka for chloroacetic acid. Again, that formula is way too long for me to write down on paper, so I'm just going to write HCA, Ca being an abbreviation for chloroacetate, and then the hydrogen being the hydrogen that the acid possesses that it donates to the water. Alright, so my reaction is going to be HCA plus H2O yields H3O plus, because this hydrogen is donated to the water, and chloroacetate. So alright, Ca minus. The initial concentration of HCA is 0.100. The initial concentration of products is going to be 0 and 0. Alright, now, I know I need to lose X on the left, gain X on the right. Well, they told me that this acid ionizes with an 11% efficiency. So that means that 11% of these molecules are breaking apart. That allows me to calculate how much hydronium I produce. So if I do 0.11 times, so the 11% times 0.1, which was the initial concentration that I was given for the acid, that tells me how much hydronium I make. And that happens to be 1.1 times 10 to the negative second. So 0 plus x is equal to 1.1 times 10 to the negative second. That means that the amount of chloroacetate that I make is also 1.1 times 10 to the negative second. And I can take that value and substitute it into the HCA column, subtract from 0.1, the amount of undissociated HCA left is 8.9 times 10 to the negative second. So these are my equilibrium concentrations. And so now if I want to calculate Ka, it's a matter of substituting these equilibrium concentrations into the mass action expression. So it would be 1.1 times 10 to the negative second quantity squared over 8.9 times 10 to the negative second. Again, I apologize for not simplifying. I just want to show you setups. Let's take a look at question number 57. 57 is giving me a sample of vinegar. It tells me that the pH is 2.90. If acetic acid is the only acid that vinegar contains, and they tell me that the Ka is 1.8 times 10 to the negative fifth, calculate the concentration of acetic acid in the vinegar. So they want the undissociated acetic acid in vinegar. All right, so let's take a look here. Okay, so with the pH, I can calculate the equilibrium concentration of hydronium. To do that, you take 10 to the negative pH power. So the hydronium concentration is going to be 10 to the negative 2.90. So let me put that in my calculator and simplify. So that's 1.25 times 10 to the negative third. That's this value right here. So that was my plus x. This is my plus x. There's going to be some minus x value over here. The amount of acetate that I should make should be equal. And so then we need to figure out what the value is over here for HA. We're going to call that a big old question mark. So that's essentially what they want us to solve for. It's question mark minus x. I don't even know if we have to do that subtraction. So how am I going to do that? Well, let's just leave this as a big old question mark. Plug these values that you have into the mass action expression. So the mass action expression, Ka is equal to hydronium times acetate over HA. I know the value for Ka. They gave it to me. I know the value for the hydronium and the acetate. What I don't know is what that denominator is. So we'll just substitute in with a big old question mark. So this is 1.8 times 10 to the negative fifth is equal to 1.25 times 10 to the negative third quantity squared over HA. And now it's just a simple algebra problem. You just have to isolate HA, and that will be your answer. All right, let's take a look at question number 59. 59. They're telling me that I have benzoic acid. Again, it's some ridiculous organic formula. I don't really feel like writing it all out, so I'm going to write HB instead. The hydrogen in the acid, B for benzoate. It's going to react with water. It's going to give its hydrogen to the water, make hydronium, and leave this benzoate anion with a -1 charge. They give me the dissociation constant in the problem. They tell me that the Ka is 6.3 times 10 to the negative fifth. They also tell me that my initial concentration of the benzoic acid is 0.050. They want the equilibrium concentrations of all of the ions present and of the undissociated acid at the end of this process. Okay, well, this is 0.050, this is 0, this is 0, because I should not have made any ions yet. I'm going to lose on the left, gain on the right. My E line is going to read 0.050 minus X for the benzoic acid, X for hydronium, X for benzoate. And so now I'm just going to take these values and substitute them into my mass action expression. So the mass action is Ka is equal to hydronium times benzoate over benzoic acid. I know the Ka value. They gave it to me in the question. I'm going to go ahead and substitute in X for the hydronium concentration, X for the benzoate concentration, and 0.050 minus X for the benzoic acid. Okay. So now I have to solve for X. I've got this ugly quadratic, and I'm going to try to cheat. So I'm going to try to apply the 5% rule and see if it works and make my life a little bit simpler. And I can do that because this value here is in the order of 1 times 10 to the negative fifth or smaller. Or it's right on the cutoff though. So I may have to go back and do this the long ways depending on whether or not the 5% rule works or not. Okay, but so I'm going to start off by ignoring this x contribution in the denominator. So let's see, 6.3 to the negative fifth times 0.05, and then I take the square root of that. So what I get for x is 1.77 times 10 to the negative third. Let's see if it was correct for us to ignore that x contribution in the denominator. So we're going to calculate the percent ionization. So what I'm saying is that this value here is 1.77 times 10 to the negative third. Alright, so if we do 1.77 times 10 to the negative third, the amount of hydrogen ions that you produced, divided by my original concentration of acid, which is 0.050, and multiply that by 100 to change that decimal to a percent. Let's keep our fingers crossed that that value is less than 5%, because then we're okay. Oh, perfect. So this happens to be 3.54% ionized, so it was okay for us to do that, so we can keep that value. So the hydronium concentration is 1.77 times 10 to the negative third, the benzoate concentration is 1.77 times 10 to the negative third, and then the amount of HB, even if you were to go ahead and subtract 1.77 from 0.050, should still be 0.050. After you apply all of the sig fig rules to that, decimal place rules. Actually, it's 0.048, but if you want to be really nitpicky about it. And that's simply by substituting this value for x over here and subtracting from 0.050. All right? Okay, let's take a look at question number 61. 61 asks me to calculate the pH of the following solutions. And I'm only going to do part A because B and C are going to be the same thing. So part A, they tell me that I have 0.095 molar propionic acid. Again, I'm too lazy to write the whole formula, so I'm just going to write HP. H for the hydrogen in the acid, P for the propionic business. It's just an abbreviation. Plus water. Hydrogen's donated to the water. You make hydronium and propionate. All right. The initial concentration of propionic acid is 0.095. I'm going to have 0 ions initially. They tell me, well, they don't tell me the Ka, but I looked it up in Appendix D in the back. So Appendix D tells me that the Ka for propionic acid is 1.3 times 10 to the negative fifth. All right, so that basically suggests to me that that's a weak acid. So I'm going to lose X on the left, gain X on the right. The key here is figuring out how much hydronium I make, because then once I have that value, I can calculate the pH. All right, so let's take a look here. So it's going to be 0.095 minus X, X. My mass action expression is going to read X squared over 0.095 minus X is equal to 1.3 times 10 to the negative fifth. Because this is 1 times 10 to the negative fifth in that range or smaller, I can choose to ignore that according to the 5% rule. We'll again have to double check ourselves to make sure that we were all right in doing that. But let's ignore it for now to see if we can make our life a little bit simpler. Alright, so what I get for X when I solve for X is 1.11 times 10 to the negative third. Let's check the 5%. Let's see if this is 5% dissociated. So if you do 1.11 times 10 to the negative third divided by 0.095 and multiply that by 100, keep your fingers crossed that it turns out to be less than 5%. Oh, perfect. It's 1.12%. So we're good. We were okay in ignoring that. All right. Okay, so then the X value, 1.11 times 10 to the negative third, is your hydronium concentration. So now you can calculate the pH. The pH is going to be the negative log of the hydronium concentration. So the negative log of 1.11 times 10 to the negative third, so what is that, 2.9 something? Alright, let's put it in the calculator. So negative log 1.11 to the negative third, oh look at that, 2.95. 2.9 something wasn't a bad guess. Alright, that's question number 61. Alright, let's take a look at 63. And by the way, for 61 parts B and C, you would do it the exact same way. You just have different compounds and different K values. 63. tells me that I have saccharin. Saccharin's a sugar substitute. It's a weak acid. They tell me the pKa is 2.32. All right? pKa. All right, well, anything that has a p in front means the negative log. All right? So what they're telling me is that the negative log of the Ka is equal to 2.32. So if I want to get the Ka out of this, then I do 10 to the negative 2.32. All right, so 10 to the negative 2.32 is 4.79 times 10 to the negative third. All right. They also tell me that I'm starting with 0.10 molar saccharin. They want the pH of this substance. All right, so at time 0, I would have 0 hydronium, 0 whatever ion that is. So, and again, I'm too lazy to write the formula for saccharin because it's some long organic thing. So I just write HS, S, some abbreviation for the word saccharin, H, the hydrogen that would be associated with that acid, plus water. The hydrogen's donated to the water, you make hydronium, and then that ion. I'm going to lose a certain amount of HS. I'm going to gain hydronium. I'm going to gain S minus. What that amount is, nobody knows just yet. I would have to do a mass action expression to figure out that value for X. All right, so let's take a look. So X squared over 0.10 minus X is equal to 4.79 times 10 to the negative third. And good gosh, I can't use the 5% rule here. All right, so how am I going to solve for X? All right, so I'm going to grab my calculator. And what I prefer to do is I prefer to do this by graphing. Let me see if I can get it to work here. Yeah, that's not doing Okay, anyways, I can't get my calculator to work right now. Not correctly anyways. You can't use the 5% rule, so you can't ignore the X contribution in the denominator. So you would have to actually graph this parabola and look for the zeros of this parabola. All right? Once you find the zeros, you ignore the negative zeros. Go with the positive zeros. That's your value for X. And once you have X, then to get the pH, just do the negative log of X. Okay? All right, let's move on to question number 65. Question 65 says to ask you to calculate the percent ionization of hydrozoic acid, and they gave me the formula, it's HN3, in solutions of the following concentrations. And so they give me 3 different concentrations. I'm only going to do part A because B and C are going to do the same thing. So for part A, I'm starting with 0.40 molar hydrozoic acid. I'm going to have 0 hydronium, 0 of this other ion, and they tell me that the Ka is 1.9 times 10 to the negative fifth. Actually, they didn't tell me it. They told me to go look in Appendix D for that K value. All right, so I'm going to lose X, gain X, gain X. This is going to be 0.400 minus X, X and X. To figure out what X is and to be able to finish off this problem, I would need to do a mass action expression to figure out what X is. So X squared over 0.400 minus X is 1.9 times 10 to the negative fifth. Because this value is fairly small, I can choose to ignore the X in the denominator, but with caution, you'd have to go back and double check yourself. So 1.9 times 10 to the negative fifth times 0.4, take the square root of it. I get an X of 2.76 times 10 to the negative third. If I take that value and divide it by 0.4 times 100 is 0.69%. So that basically allows, so the 5% rule checks out. We're okay to have ignored that. Okay, so X is 2.6 times 10 to the negative third. So that, to calculate the percent ionization, it's the hydronium that you make divided by the original amount of undissociated acid times 100. So the hydronium that I made was 2.76 times 10 to the negative third. The original amount of undissociated acid is 0.400 minus 2.6 to the negative third, or 3.97 times 10 to the negative first. Let's see. And so you simplify this on your calculator and multiply it by 100 to change it from a decimal to a percent, and that would be your percent ionization. All right, let's continue here. Question 73. Question 73 is, it gives me some chemicals, and they want me to write the chemical equation and the Kb expression for the ionization of these substances. These are bases. If they want Kb, treat it as a base. All right. So the Bronsted-Lowry definition is that bases will take hydrogens from water. So you're going to take a hydrogen from water and give it to this compound here. Compound A is also called dimethylamine. So when you write the conjugate acid for dimethylamine, you would write CH3 parentheses 2 NH2 plus, because you've gained a proton, so it needs to have a +1 charge, plus OH minus. The mass action expression Kb would be CH3 2 NH2 plus times OH over, oops, let me move this over so you can see it, CH3 2NH. I'm not going to write the Kb expressions for the other two equations. I'm just going to write the reactions. There's no need for me to do this. I think by now you've realized that for mass action expressions for Kb, you put products on top, reactants in the bottom, the coefficients become powers, and you don't include water in any of these expressions. All right, let me show you how carbonate reacts with water. So again, carbonate is going to steal a hydrogen from water, and then you're going to make HCO3 1 minus plus OH. And then this last one, the formate ion, CHO2 minus, steal a hydrogen from water, is going to become CH2O2 plus OH minus. Alright, and the reason why it doesn't have a charge is because it was -1 initially. When you add a hydrogen, you add a plus 1 value to that charge. Alright, last two problems. Question 75. It says calculate the molar concentration of hydroxide ions in a 0.075 molar solution of ethylamine. They tell me the Kb is 6.4 times 10 to the negative fourth. They want me to calculate the pH of the solution. Alright, so I need a Rice chart. My initial concentration of ethylamine, again I gave it some generic abbreviation just because I'm too lazy to write the formula for ethylamine. Plus water yields HEA plus. So that is this ethylamine having taken that hydrogen from water. And the reason why I knew to steal the hydrogen rather than to donate the hydrogen was because they gave me a Kb value. I'm going to treat this substance as a base. And the Bronsted-Lowry definition of bases is the bases are hydrogen thieves, not hydrogen givers, right? Okay, so I'm going to make HEA plus hydroxide. So my initial concentration of ethylamine is 0.075. Of these ions, it's 0 and 0 because it does it very weakly. This value is less than 1. So I'm going to lose X on the left, gain X on the right. My E line is going to read 0.075 minus X, X. If I want to figure out what X is, I'm going to have to do X squared over 0.075 minus X is equal to 6.4 times 10 to the negative fourth. And just like in question number, let's see, which one was this? 63, we are not going to be able to apply the 5% rule because that K value is too big. So you're going to have to actually solve for X using the quadratic formula. And I don't really feel like doing it right now because it is 3:30 in the afternoon. I want to go home. So once you solve for X, X will be your hydroxide concentration. That will allow you to calculate pOH. So once you have the hydroxide concentration, you do the pOH by doing the negative log of X. They didn't ask for the hydroxide concentration. They really wanted the, or they didn't really ask for the pOH. They wanted the pH. So once you have the pOH, take that value and subtract it from 14 to get your pH. Alright, so that's how you do 75. Alright, 77. It says, Ephedrine, a central nervous system stimulant, is used in nasal sprays as a decongestant. This compound is a weak organic base, and they give me this long, drawn-out organic formula. Again, I'm too lazy to write it, so instead I'm going to abbreviate E. It interacts with water. It's a thief. It steals a hydrogen from water, and when it steals a hydrogen, it turns into EH+, and it leaves behind hydroxide. They tell me that I have a 0.035 molar solution of ephedrine. It has a pH of 11.33. What are the equilibrium concentrations of all of these things? What's the hydroxide concentration? And then calculate Kb for the ephedrine. My problem with this question is that it's a base. I've shown it as a base, yet they're using pH numbers to describe it. And so that makes me uncomfortable. I would prefer to deal with pOH values. But that's simple enough, because to get pOH from pH, you just subtract from 14. So 14 minus 11.3 is 2.67. All right, fabulous. If I have the pOH, I can figure out the equilibrium concentration of hydroxide simply by doing 10 to the negative pOH. So 10 to the negative 2.67 is my hydroxide concentration. So I get a hydroxide concentration of 2.14 times 10 to the negative third. So that's this value right here. And actually, if you remember, we lose on the left, gain on the right, gain on the right. If this value is going to be equal to that value right there, so to the conjugate acid, they're going to be equivalent. And then to calculate the E, I would do 0.035 minus 2.14 times 10 to the negative third. Or 3.29 times 10 to the negative second. Alright, so those are all my equilibrium concentrations. So if I want to figure out what Kb is, you just substitute those values into the mass action expression. So 2.14 times 10 to the negative third times 2.14 times 10 to the negative third over 3.29 times 10 to the negative second. Okay. Alright, so that's it for this recording. If I made any mistakes, please don't crucify me in my absence. And then for the rest of the period, please work on the assignment that's on the board, the honors pages that I've asked you to read, and the questions that I've asked you to go over. I've left this answer key with the sub in the event that you want to look at it with greater detail. And if I've made any mistakes in this, please just take a note of it. We can talk about it when I return on Thursday, assuming that I can talk. Okay? See you. Bye.